Good morning, everybody. So I just want to take a little bit of time and talk about something that we find in our books. It's at the very end of section 2 in chapter 11. This is something called Archimedes Principle. Now, to understand Archimedes Principle, we first have to talk about something called buoyancy or the buoyant force. Now, remember in the past we talked about the fact that as you go deeper underwater, your fluid pressure is going to increase. So here I've got a 500 Newton block of metal. All right, we'll just say it's a block of steel. All right, and you'll see that on top of the block of steel, when I put it underwater, there's some pressure pushing down on top. In fact, the whole block is going to be surrounded by water pressure. Now, the deeper you go, the greater the pressure is going to be. So there's going to be more pressure under the block than there is on top of the block because the bottom is just slightly deeper under the water. And so because of this, you get a net force. In other words, you have unbalanced forces, weaker forces at the top, greater forces at the bottom, because there is more fluid pressure beneath the block than there is above the block. Okay, and that difference in fluid pressure is going to create what we call the buoyant force, or BF. Okay, so that is going to be the net force acting in an upward direction on any object. It doesn't matter what it is. All objects, when placed in a fluid, are going to have a certain amount of buoyant force pushing up on them. Now, if that's true, the question becomes, why is it that all objects don't just float? If all objects have a buoyant force pushing up on them, why don't all things float? And the answer has to do with another force that's acting in the opposite direction of the buoyant force. Can you guess what it is? It's gravity. Okay, so any object that you place in a fluid, like water, is going to automatically have both of these forces acting on it. The buoyant force acting in an upward direction, and gravity acting in a downward direction. Now, what's going to determine whether this object sinks or floats is all going to be determined by which force wins out. Okay, so the force that's greater, in this case, we just eliminate all these little lines of force, okay? So we're asking a question, in this case, which is greater, the buoyant force or gravity, okay? So I've written on here that I've got a 500 Newton block of steel, okay? Let's just say, for the sake of argument, that the buoyant force is only 300 newtons, okay? So the force of gravity is 500 newtons. The buoyant force is only 300 newtons. If that's the case, my object is going to sink, okay? Even though it still has a buoyant force acting on it of 300 newtons, in this case, gravity is winning out. It's greater. Okay, now when we're talking about Archimedes' principle, and you can find this on page 428 in your books, what Archimedes says is the buoyant force acting on an object is going to equal the weight of fluid that it displaces. All right, so let's think about that. When we talked about displacement way back in chapter 1, we're basically talking about the fact that any solid object, when placed in a fluid like water, is going to push aside that water. It's going to displace it, all right? So let's imagine when we put this 500 Newton block in the water, it's pushing aside or displacing a certain volume of water, okay? If the buoyant force acting on this block is 300 newtons, then I automatically know that the weight of this fluid is going to equal 300 newtons and vice versa. the other way around. Okay? So Archimedes' principle states that the buoyant force acting on an object submerged in a fluid is going to equal the weight of the fluid displaced. Now, if the weight of that fluid displaced is less than the weight of the object is going to sink. Let me give you another example. Okay, the beginning of the book talks about the Titanic. All right, so here we have the Titanic. Now, the Titanic is a massive steel ship. Okay, let's say for fun, for the sake of argument, it weighs 1 million newtons. Okay, in other words, that's going to be the force of gravity pulling down on the Titanic. Okay. Okay, gravity is pulling down on the Titanic. That means in order to stay afloat, the Titanic has to displace more than 1 million newtons of water. Okay? So let's say we were to take this amount of water, right, that the Titanic displaces. All right? We'll say we'll take that and we'll put that over here. All right, everything that the Titanic pushes aside when you put it in water, right, this is going to be the amount of water displaced. So in order for the Titanic to stay afloat, that amount of water that is displaced by the boat has to be greater than the weight of the ship. So let's say the Titanic displaces 1.5 million newtons of water. All right, so when you put this boat in the water, it's going to push aside 1 million newtons of water. That means that the buoyant force is going to equal 1.5 million newtons. Okay? So if the Titanic displaces 1.5 million newtons of water, the buoyant force is 1.5 million newtons. That's Archimedes' principle. The buoyant force equals the amount of water displaced. All right? And as long as the amount of water being displaced by the Titanic is greater than its weight, the object will float. The problem is, and this was the problem for the Titanic, is if the weight of the object increases, and if it gets to a point where it's greater than the buoyant force, it's not going to stay afloat anymore. And pretty much what happened with the Titanic is when it got that giant gash in the side of it, something changed, all right? All these forces were no longer in balance anymore, and the Titanic started taking on water, all right? The moment the weight of the Titanic increased above the buoyant force, it started to sink. Why? Because gravity was now greater than the buoyant force. Because that's what happens to any object. As you add more weight to it, gravity is pulling it down with greater force. If that gravitational force overcomes the buoyant force, the object will sink. All right? So this is what Archimedes' principle is all about. It's all about having that balance between the force of gravity and the buoyant force pushing from beneath. Okay, just to give you another example of this, what I've set up here is I've got a scale, a rock, a little Christmas pie tin, and a graduated cylinder that's completely full of water, like all the way up to the brim. All right, so first what I'm going to do is I want to get the mass of my rock here. All right, so I'm going to take my rock, put it on the scale, and I see that it has a mass of 193.9 grams. okay? In order for this rock to sink or float, it's all going to depend on how much water it displaces, okay? So if the water has 193.9, let's do that again. 193.9 grams, that means in order to float, it has to displace over 193.9 grams of water. We'll see if that happens. Okay, so first what I'm going to do is I'm going to take my little pie tin and I'm going to zero out the scale. All right, so my scale is reading 0. That means whatever I put into the pie tin, I'm only getting the mass of that without the pie tin. So I've just subtracted that. So I'm going to take my graduated cylinder very carefully. All right, and I'm going to put my rock in. You see, as I'm doing that, that rock has just displaced or pushed aside a certain amount of water, and it's overflowed into the pie tin. Now I'm going to very carefully take this out. All right, and whatever water I have in the pie tin, that's the amount of water that this rock has displaced, okay? That's the fluid that has been displaced. That's going to be equal to the volume of my rock, all right? And I can see this rock only displaces 82 grams of liquid, okay? That is not nearly enough liquid to get my rock to float, and so you can see it's going to sink. Actually, what's going to happen is my rock is going to get stuck about halfway through, all right? But that's not floating, it's just gotten stuck in my graduated cylinder, all right? But that's the idea behind Archimedes' principle, is that the buoyant force acting on an object is going to equal the amount of fluid displaced. So what I've just found here is the fact that this rock is only going to displace about 82 grams of fluid, not nearly enough to get it to float.